In this tutorial, we're looking at section 7.6 on curve sketching. Okay, so now that we've worked out how to find our derivatives and our second derivatives, we basically have everything that we need to be able to sketch our graphs. Okay, so I've got a list of things that we need to do in order to fully sketch our graphs. Okay, so this is assuming we've already drawn and labelled our axes. Then we need to find the y-intercept by letting x equal 0. We need to find the x-intercept by letting y equal 0. We need to find the first derivative. Find our derivative of our function. We let f dash of x equals 0 and solve for x. This will give our x coordinates as stationary points. Okay, we need to complete a gradient table to identify if your stationary points are max, min, or point of inflection. Okay, a stationary point of inflection, that is. We need to substitute these x values of the stationary points back into our original function f of x and to give it our y coordinates of our stationary point. Okay. We need to find the second derivative. Okay, and this is only if we're degree 3 or higher for our polynomials. For our trig functions, things like that, we can still do it. Our second derivatives tell us where non-stationary points of inflection are. Okay, so a point of inflection is where the tangent goes from being on top of the curve to below the curve or vice versa. It can be thought of as the point where the graph changes from being concave up to concave down. Okay, so we find the second derivative, solve for x when the second derivative equals 0, and sub this value into f of x and solve for y. So what we mean by this part, okay, is if we've got a graph like this, okay, well our tangent is above our curve, it's above our curve, it's above our curve. Okay, but at some point here, okay, in the middle, okay, we're going to switch and our tangent's going to be below our curve. So our non-stationary point of inflection is this point in here, okay, where it switches from being on top to being below. This is our tangent to our graph. Okay. Okay, we need to identify any asymptotes. Okay, so if y is in the form of y equals 1 over ax squared plus bx plus c, okay, if the determinant is greater than 0, the graph will have 2 vertical asymptotes and 1 turning point and no points of inflection. Remember, our determinant is b squared take 4ac from our general quadratic formula. The x-intercepts of ax squared plus bx plus c will become the vertical asymptotes. Where ax squared plus bx plus c is above the x-axis, 1 over that will also be above the x-axis. This is also true for values below the x-axis. So where this is below, this will be below. Where this is above, this will be above. If g of x, which we're saying is this part, okay, crosses the y-axis at 0a, okay, then y equals 1 over ax squared plus bx plus c will cross at 0 and 1 on a. Okay, so basically we're just saying that really this is probably better if we call that c, okay, because it's our c value here, okay, then we'll cross at 1 on c, okay, for this graph. If ax squared plus bx plus c approaches approaches infinity, okay, then 1 over ax squared plus bx plus c approaches 0 from above. So it means as this approaches infinity one way, okay, well 1 divided by infinity, okay, is going to be 0. Okay, so if we approach a positive infinity, okay, then we're going to approach our asymptote from above. Okay, if this approaches negative infinity, then this is going to approach 0 from below. So we're talking about horizontal asymptotes in this part. Okay, if ax squared plus bx plus c has a local maximum at pq, then 1 over ax squared plus bx plus c will have a local minimum at p and 1 over q. Okay? And if we have, this part has a local min at pq, then this will have a local max at p and 1 on q. Okay. If f of x is in the form of f of x equals p of x over q of x, where p of x and q of x are polynomials, okay, when p of x, the top one, equals 0, then we get the x-intercepts of f of x. Okay, the y-intercept is still found by letting x equal 0. Vertical asymptotes are when our denominator equals 0. Okay, vertical asymptotes can never be crossed, but remember horizontal asymptotes can. If the degree of p of x is greater than the degree of q of x, then we divide p of x by q of x to get an expression in the form of S of x plus Rx over Q of x. Y equals S of x is the equation of the asymptote. Okay? If S of x is a constant, then we get a horizontal asymptote. If S of x is linear, then we get an oblique asymptote. Okay? If S of x equals ax squared, we get a quadratic asymptote. Okay? So a few different types of asymptotes that we haven't seen before. Okay, so we're going to have a look at worked example 21. Okay, so we've got sketch a graph of the function y equals x cubed plus 6x squared plus 9x. Okay, and we know our domain is R. Okay, find the coordinates of all axis intercepts and stationary points and establishing their nature. Also find the coordinates of the points of inflection and find and draw the tangent to the curve at the point of inflection. Okay, is what the example says. Just thought, let's just make it a bit more straightforward and let's just say we're going to sketch it. Okay, so what we can do for this, okay, is first of all we can take x out as a common factor and say we've got y equals x outside of x squared plus 6x plus 3. Okay, we can see, we should be able to see, sorry, plus 9. I'm jumping ahead because we should be able to see that we can make that x outside of x plus 3 squared. Okay. So we want to find our x-intercepts. So that's quite easy from here. Leaving y equals 0, we can use the null factor law. So we can say x-intercepts, okay, are going to be at x equals 0, okay, and at x equals minus 3. Okay. So from our knowledge of cubics, hey, we know we should be aware that this one will cross our x-axis, it will actually cut it. This one will actually be a turning point on the x-axis because it's a squared one. Okay, if this term was cubed, okay, then we'd have a stationary point of inflection at our -3. Okay. Also we know that our x-intercepts, well, y is also 0, so we can say we go through 0, 0 and, sorry, I won't write that. We can say that we go through the points 0, 0 and minus 3, 0. Okay, if we're going to find our y-intercept, we've got to let x equal 0, and you'll see, well, we already know that our y-intercept is 0, and you can confirm that by seeing that everything would drop out. What we need to do is find the first derivative. Okay, so what we're going to do is start up here and say, well, dy dx, well, that's going to equal 3x squared plus 12x plus 9. Okay, well, we can say that our dy dx equals our 3 outside of x squared plus 4x plus 3. Okay, and we can see that that's going to be 3 outside of x plus 3, x plus 1. Okay, so we can see that we're going to have stationary points, okay, at x equals minus 3 and x equals minus 1. Okay, so we don't know what these stationary points are yet. Okay, but we can actually have a bit of knowledge here and think about this pretty logically. Okay, so we know that this is a positive cubic. Okay, because the sign out here is positive. Okay, so our positive cubics are in that form. Okay, so we know that our -3 would actually be a max and our -1 would be a min. Okay, what we also need to do though is find the y coordinates at these points. Okay, so we need to put in our -3 in for our equation here. Okay, and so we find, and our -1, when we do that, we find our stationary points at -3, 0, and at -1, -4. Sorry, -1, -4. Okay, by subbing these values back into this equation. I'm not going to do the working out just to save a bit of space. Okay, we need to find the second derivative, so we can find this point in here where we change. Okay, so when we do that, we get, well, we knew our dy dx is this, so we'll use this form, it's the easiest. So we can say d squared y on dx squared, well, that's going to equal 6x plus 12. Okay, when we set that equal to 0, Okay. Oh no, sorry, we won't do that. We'll just take our 6 out as a common factor. 6x plus 2. Okay, so we can see our point of inflection is going to be at x equals minus 2. Okay, so what we can do is we could do our derivative test on these points here, on our stationary points, to get these max and min values. Okay, but we can use our knowledge of the fact that it's positive cubic to actually not worry about doing that. Okay, if we did do that, remember what we need to do, the process is pick values either side of both of our stationary points, okay, and see what the gradient is to see if it's positive or negative, and so you can start getting a shape of your graph. Okay, I'm not going to do that because we know what it is. Okay, we want to find, well, yeah, we found our point of inflection here, but we haven't actually put in that back into our original graph, original equation, sorry. When we do that, we find the point of inflection is actually -2, -2. When we put in -2 into here, we get -2. Okay, so we're building up the information that we need. Okay, what we want to do is determine the gradient, okay, at our point of inflection. Okay, we can do that as well. So our gradient then, okay, when we sub this into our derivative function, we find is -3, okay, which confirms our negative gradient down there. Okay, so we're pretty much organised now. Okay, they did actually say in the worked example about sketching the tangent at our point of inflection, which we could do if we like. Okay, because we know our m value, we know our x1 and our y1 value, so we can put them into our equation of our tangent. Now I'm not going to worry about doing that. Okay, we're just going to sketch the graph now. So we know that we just do a couple of straight lines just so our axes are at least somewhat decent. Okay, we know we've got y and we've got x. Okay, we know that we've got an x-intercept here and at -3. So down here at -3. Okay, we also know that we have stationary points here, okay, and at -1, -4. Okay, and we knew, as we said earlier, that we knew this one was a turning point. Okay, here because of the squared term. Okay, that's been confirmed with here. Okay, saying that we have a turning point here. Okay, and we know our point of inflection is at -2, -2. Now that's not going to matter too much. Okay, but so we know we're going to come up, just touch here, come down to here, right, and then we're going to come back up through here. So we can start to sketch it now. So now we're going to come down. Okay, it's not the best graph I've ever done, okay, but you get the idea of the general shape. Now remember, your graphs should be a lot neater than that because you're going to do them with pencil, okay, so you can neaten them up as you go through. Okay, so we're going to have a look at this next worked example. Okay, so again we want to sketch a graph of y equals 6x squared minus x to the 4. So the first thing we're going to do is say, well, y equals x squared outside of 6 minus x squared. Okay, so we get a better idea of what's happening here. Okay, so we can say then that x squared outside of √6 take x times √6 plus x. Okay, so you can get an idea what's going on. Okay, so what we want to do is find our x-intercept. Okay, so we're saying our intercept, x-intercepts, okay, is going to be, well, when x equals 0, when x equals √6, and when x equals -√6. Okay, so we know those coordinates in are 0, 0, okay, √6, 0, and -√6, 0. Okay, no point doing our y-intercept, okay, because we know that we are going through the point 0, 0, so it will be our y-intercept. Okay, what we will just note is square root of 6 is approximately equal to 2.45. Okay, it's always best to approximate any exact values or surds as a decimal, just to get a bit of an idea where they fall on the number line. Okay, so now we can find our first derivative. Now we're going to go off this part. Say our dy dx is equal to 12x minus 4x cubed. Okay, again, we can bring a 4x out the front, leave us with our 3 take x squared. Okay. So that means then we can factorise this and say it's 4x outside of root 3 take x root 3 plus x. Okay, so that means that we get stationary points. Okay, so we get stationary points at x equals 0, x equals root 3, and x equals minus root 3. Okay, when we sub these points back into this original equation to get the y coordinates of our stationary point, okay, then we find that we have our stationary points at 0, 0, at root 3, 9, and at minus root 3, 9. Okay, so we're getting there. Okay, so we need to find our second derivative now. Okay, so this was our first derivative, so now we do d squared y on dx squared, okay, which is going to equal 12 minus 12x squared, which is 12 outside of 1 minus x squared. Okay, which means we can say we've got 12 outside of 1 minus x and 1 plus x. Okay. So what we can do here again is we can think about this. Okay, our quartic here is a negative quartic. Okay, so which means it's going to look like that. Okay, now we're saying that we've got stationary points at 0, 0, so we're going to expect that it's going to look something like this. There's our 0, 0 stationary point. This would be our root 3, 9 stationary point, our negative root 3, 9 stationary point. Okay, again, we know we go through 0, 0. This would be our negative 6 root 6, 0. This would be our positive root 6, 0. So we've really got a good idea of what's happening here. Okay, so we don't really need to worry about doing too much more. Okay, we do need to, we've got this here. Okay, so we also know then at these points that at negative 1 and x equals positive 1, okay, that these are our non-stationary points of inflection there and there as well. Okay, so that's where we're going to have a maximum gradient, okay, and where we're going to change. Okay, so now we can draw some axes again. Draw our graph. Okay, might make this one a little bit longer. Okay, so we know we go through negative root 6. We know we go through positive root 6. Okay, we know we've got a stationary point at negative root 3 and a stationary point at root 3. We know we go through here. Okay, we know that's going to be just a turning point because it's our squared term. Okay, and we also know up at these points that we're going to go through here and here. Okay, that's up at 9. Okay, so we've got all the information we need now to sketch our graph. Go through that turning point, come down, go through this turning point, then back up again. Through here. Okay, and we know that at 1, okay, we go through here, sorry, negative 1 and positive 1 will go through here, and they're our non-stationary points of inflection. If we, sorry, we've got to do that. If we sub these back into the original, we get the points -1, 5. Okay, and 1, 5. Okay, so we know that there is 5. Okay, again, your graph will look a bit better than that. Okay, because you'll use pencil. Okay, we'll keep moving on. Okay, so we're going to sketch the graph of y equals 24 over x squared plus 2x take 24. Okay, we'll need to state the equations or any asymptotes. Okay, find out intercepts and turning points, etc., etc. Okay, so what we're going to do is we're going to factorize the domain to the denominator to start off with. So instead of y, I'm actually going to say f of x this time. So we're going to say f of x equals our 24 over. When we factorize this, we should see that we're going to be x plus 6, x minus 4. Okay, so remember when our denominator equals 0 is where we're going to get vertical asymptotes. So we can say we've got vertical asymptotes at x equals minus 6, okay, and x equals positive 4. Okay. We want to find out x-intercepts. Okay. So problem that we've got there is when y equals 0, then we'd multiply everything across, okay, and we're going to end up with 0 equals 24. Doesn't make sense. That means that we have no x-intercepts. Okay, we have no x-intercepts. Okay, if we don't have any x-intercepts, you would assume then that we're going to have a horizontal asymptote at some point. Okay, namely the x-axis, but we need to confirm that. Okay, we need to find the y-intercept. So when x equals 0 in here, then we're 24 over minus 24. So we're going to have y-intercept. Okay. Okay. At 0 minus 1. Okay, so we've got that worked out now. Okay. Find the equations or any other asymptotes. So we think, okay, as this gets really big, what's going to happen? Okay, as this gets really large, okay, then we're going to end up approaching from the positive side. We're going to end up with positive. Okay, so when this approaches positive infinity, we'll start with positive infinity. Okay, well, positive squared, positive. Okay, 2 times the positive, we're still positive, really big number. The 24 minus 24 doesn't really matter. We're going to be a positive number over a really large positive number, so we're going to approach, okay, 0 from the positive direction. So as f of x approaches positive infinity, okay, then sorry, not f of x, as x approaches positive infinity, f of x is going to approach 0 from the positive side. Okay, and we say as x approaches negative infinity, okay, well, when say negative infinity squared, okay, it's going to be a really big number, a really big positive number. Okay, we'd need to take away 2 lots of infinity, but infinity squared is bigger than 2 lots of infinity, if you like. Okay, so this is still going to be positive. Okay, so that means that f of x will still approach 0 from the positive side. Okay. The plus indicates that okay, so we also can gather from that, okay, that we have a horizontal asymptote at y equals 0. Now, if we were to approach, if something had happened differently and we were to approach, say, 1 from the positive side, okay, then we would have had a horizontal asymptote at y equals 1. If we were to approach 2 from the positive side, then horizontal asymptote at 2. Okay, so we need to differentiate the function now. Okay, so what we can do is we can say, well, I might actually change colours for this next bit. Okay, we can say, well, f of x, it's equal to 24 outside of x squared plus 2x take 24 to the power of negative 1. So f dash of x. Okay, we've got to use the chain rule, but we do our quick way. So we go, our negative 1 times our 24 gives us our negative 24. We'll times that by the derivative of what's inside here, which will be 2x plus 2. Right, and that gets times by x squared plus 2x take 24 to the power of negative 2. Right? So that means that f dash of x is now going to equal negative 24 outside of 2x plus 2 over our x squared plus 2x take 24 squared. Okay. Stationary points occur when the gradient is equal to 0. Okay, well this is going to be equal to 0 when this part's equal to 0. Okay, not when this part's equal to 0. When this part's equal to 0, it's undefined. So we want when this part's equal to 0. So basically we're saying, well, 2x plus 2 equals 0. So that means that x equals negative 1. Okay, so we know we've got a stationary point at x equals negative 1. If we sub negative 1 back into this equation up here, okay, then we find our stationary point occurs at negative 1 and negative 24 on 25. Okay, so not a great part, but anyway, we're getting there. So when we look back at this, okay, and we look just at this part here, okay, it's a positive quadratic, this part here, okay, which means its turning point would be a local minimum, okay, because it's a positive quadratic. So this means this is a local maximum. Okay, so we're getting there now. Okay, so now we've got all the information we need to be able to actually sketch this. Okay, so we'll draw up some axes quickly. Okay, so we know we've got vertical asymptote at 4. Okay. So around here at 4, vertical asymptote. So vertical asymptotes, remember, or any asymptotes are represented by a dotted line. Okay, usually red. Okay, for no real reason, it's just that by convention we usually use red. Okay. So draw those on. Okay. The ones that are always tricky to show, and people forget to show them, are our horizontal or vertical asymptotes that are the axes. You just need to get your dotted line extending past a little bit. Okay, we also need to think about our other information that we know. Okay, we know that our y-intercept was at negative 1. Okay, so we know that was 4 and that was minus 6. Okay, we also know that we had a local maximum at negative 1 and negative 24 on 25, so that's just going to be a smidgy bit higher than there. Okay, we know that when we approach the as x approaches positive infinity, okay, so if we go this way, then we're going to approach 0 from the positive way, so we're going to come down this way, so it means that we're actually going to look like this. Okay. We know the same thing happened when we went towards negative infinity, so we can say that we're going to come down like this. Now if you have a bit of trouble with actually working out what the shape of this is going to be, okay, you can always pick some other points, like sub in some other points. If you go, okay, hang on, I'm not sure if it's going this way or not, okay, or this way. We know asymptotes, so we know we're going to approach it. Okay, well, we should remember that we know that we're coming from this way because it was from positive, and we know we don't have any x-intercept, so you should realise it doesn't go this way. Okay, but sometimes it can be hard to get our head around the shape of them, so just pick some other points, okay, that you want to know so you can plot them. Okay, and we know we're going to come up, okay, have our maximum there, start coming back down this way. Okay, that's what our graph looks like. And of course, don't forget to label your axes. Okay, so we'll keep moving on. We've got one last worked example. Okay, so this is worked example 24. Sketch a graph of y equals x cubed, take 54 on 9x. Hey, so first of all we need to axis intercepts. Okay, so what we're doing is we're looking at the here. Okay, when this is equal to 0, we'll get our x-intercepts. Okay, so you say, well, x cubed equals 54. So x equals the cube root of 54. Okay, so really we're saying that the graph crosses there. Okay, so we're saying that we've got an x-intercept of cube root of 54, 0. Okay, that's really not that convenient saying that. So what we'll say is it's 3.780. Okay, so that's our x-intercept. Okay, for our y-intercept, we're going to let x equal 0. Okay, that's no good. Okay, because it's going to be undefined there. So we realise that we've got to have no y-intercept. Okay, which means we've got a vertical asymptote at x equals 0. Okay, so we've got a vertical asymptote there. Okay, so what we need to do is we can simplify our expression. Okay, here we can split up into two parts. So we can say that y equals x cubed over 9x minus 54 over 9x. So we can say y equals x squared on 9, take 6 on x. Okay. So we're looking then as we want to find the equation of any other asymptotes. So we say as x approaches infinity, okay, as x approaches infinity, okay, then y approaches, okay, so this is going to drop out, okay, this term, okay, because we're going to be making this essentially 0. This is going to be a really big number, so we're going to be approaching it from below. Okay. And then we're saying as x approaches, below, that's yeah, sorry, as x approaches negative infinity, sorry, we just missed that in the textbook. Okay, we're going to be approaching from above. Okay, so we see that our quadratic here is actually going to be an asymptote. So we're going to have an asymptote, right, of y equals x squared on 9. So something a little bit different to what we usually have. Okay, so we need to find our derivative. Okay, so we can use this form to find our derivative. I might do that up here this time. So what we're going to do is we're going to say, well, I might change colours actually just to split things up a bit. So say y equals x squared on 9, take 6 times x to the negative 1. Our dy dx is going to equal 2x on 9, okay, plus 6 over x squared. Okay, remember our negative 1 comes down the front, makes it positive. Take 1 away, make it negative 2, which we can write it like that. Okay, so stationary points are when this equals 0. Okay, so we're going to say when 2x on 9 plus 6 on x squared equals 0. Okay, so really we're going to say 2x on 9 equals minus 6 on x squared. Okay, so we can say then when we do that, we can rearrange and say, well, x cubed equals minus 27. So minus 27. Okay, so x is going to equal minus 3. Okay, so we're going to get a turning point at -3. Okay, when we sub -3 back into here, we get +3, so we get a turning point at -3, 3. Okay, so we're getting there. So basically, we've got everything that we really need now, okay, to actually graph this, believe it or not. So it's a little bit weird, this one, because of our equation of our asymptote. So we'll get some axes going. So really, when you get an equation of an asymptote that's a quadratic or something like that, you really need to be thinking, well, hang on, I've got to sketch that quadratic first. Okay, so really though, what's not too bad about this is, thankfully, it's just x squared on 9, so that's just a dilation factor. Remember, dilation factors you really don't see that much. We haven't been translated or anything, so really we can say that we've got our quadratic here. Okay, that is our asymptote. So again, I'm doing it as a dashed red line. Hopefully it's something like that. Okay, and we know we've got our x-intercept at our 3.78, so we could say that somewhere here. Okay, and hang on, we also need to remember, I almost forgot, we've got a vertical asymptote as well, going on down here. Okay, so we know we need to approach our asymptote, so we can come this way. Okay, and we also know, as we are approaching positive infinity, we're going to approach our asymptote from below. So we're working in well here. It's going to be something like this happening. Okay, I probably haven't done that very well. Okay, we should be a little bit smoother through there. Sorry about that. Okay, and then we also know we've got a turning point at -3, 3. So we're going to be in here somewhere. Now we know we approach this asymptote from above, so we're going to come this way. Okay, we know we've still got this vertical asymptote that we're going to approach as well. So it's going to come up like that. Okay, so this should have been a little bit more just like that. Okay, so I didn't draw that one very well, so it should have been a little bit more like this one here. Okay, but look, that's everything that we've got for curve sketching. Generally speaking, we really have most of the skills we need to do this before we worry too much about the second derivatives. They do talk about the second derivatives, okay, but it doesn't matter that much, to be honest. You can actually get all the information you need, okay, without it. The only thing that you may need, and be specific to the question, would be those non-stationary points of inflection. Okay, that's the only thing that you really need this second derivative for. You can already work out the nature of your stationary points either from our first derivative test or our knowledge of the actual function itself. Okay, so look, hopefully there's enough to get you through. Okay, make sure that you really get sketch and graphs down well. You don't want to lose marks with sketch and graphs. Okay, if you know the shape, you've worked everything out, you really want to make sure that you're not losing marks for a messy, untidy graph, because it's just silly marks to lose.